All right, so let's talk about the impact studies a little bit and then mitigation. Um, there is an IEEE standard guide on this IEEE 1547.7, and this was published in 2013. And what this does is it provides some, I guess, checklists for what you need to look at for a DER interconnection. And so this was including things like potential for unintended islanding. We talked about that before. Impact on equipment loading. Obviously, you don't want to burn out any cables or transformers. Impact on protection design, whether that's going to cause issues with coordination. Voltage regulation is a huge area. Maybe this even ties into reactive power management. And then these things we talked about related to power quality, like flicker and sags and swells, these rapid voltage changes, and also harmonics. And one thing you got to realize about this topic area is it's still in flux. So when we started doing these studies, probably started in the latter part of the 2000 era, like maybe 2006, 7, and 8, and we were starting to look at impact to megawatt units. We didn't have any existing units out there to benchmark against. And so this is just kind of our best guess in the latter part of the 2000s as far as what should even go into these impact studies. And then as we got more installations in the field and we kind of learned from that, we've been kind of tuning up what needs to go into a study. Initially, we had a lot of smaller units. What I mean by small, like hundreds of kilowatts and megawatts. Now we're seeing at the distribution level, maybe up to say like 20 megawatts. So not only are we getting more experience based on past projects, but we're also seeing the impact of very high penetration levels. And we're taking this knowledge and we're actually factoring this back into the thresholds we use in our studies. And so 2013, this is a pretty antiquated standard, especially given that with the 1547 2018, these inverters have a lot more capability that we can include in our modeling. So I'm going to talk a little bit about what's in the 2013 standard, and I think a lot of this still applies today, but just realize that this is sort of an evolving sort of a topic area. And if you had like an example from 2018, I mean, we've learned a lot of things since 2018, is what we ought to be looking at criteria in these different types of studies. So from 1547, what they gave is they provided a checklist, and it showed all the different sort of things you can look for. And so you had different sort of sections in here which went into these checklist items. And I'm not gonna try to go through this particular table, but I just want you guys to know that that's what's in this particular document, is all the different sort of things that DER could impact. And these are all would be possibilities for what to include in your particular impact study. In general, and based on this 1547.7 guideline, as well as kind of other interconnection study guidelines, usually what people start looking at is they start looking at steady state power flow. As I mentioned before, what PV or DER does is it causes backfeed into the grid, right? A grid that was originally designed to operate unidirectionally. And so typically what you're doing is you're looking, what sort of impact that has on the feeder. A lot of times what you're going to do is you're going to look at feeder peak loading conditions like your summer and winter peak, as well as minimum loading conditions. And the reason you want to look at this is DER is say if it's solar based, it's going to have its peak injection at noon, right? And what you'd really be worried about is what's happening at noon on a fall or spring day when you have your light loading conditions, right? So there's usually these different corner cases that people look at, usually peak conditions with DER peak and non-peak, and then the off-peak minimum loading conditions where you have DER peak and off-peak. So you're going to look at, what's the impact on reverse power flow? Are you going to be overloading any components? Whether the voltage is going outside the plus minus 5%, do you get a lot of imbalance if you have single phase DG? What's the impact on losses? This is the sort of thing that you would initially start with when you're running, say, like a power flow program. We'll do the same thing in our project part 3 as well. If you're worried about the protection, then this is where you would run some short circuit analysis. You'd be looking at the grounding. That's going to have an impact on short circuit currents. And you're wanting to make sure at the starting point that you're not going to overload any circuit breakers. And so what can happen is if you had a substation and you have a substation transformer, if you have like parallel circuits, what can happen if you had DG on this feeder, let's say, and you had a fault over here, well, this DG can backfeed through that circuit breaker, and you're going to have that current plus the original current, right, which could actually cause overloads on circuit breakers. So that another thing you do as well is you'd have to do some short circuit analysis. The other thing you look at is you look at dynamic voltage analysis, where basically you're looking at the voltage flicker due to the cloud cover. You're looking at step voltage changes due to DER trips and restoration events. Maybe you're looking at interaction between your DER and capacitor bank switching and regulator operation. This is kind of hard to do in a snapshot program like Windmill that we're using for class now. And so we're going to be using a different tool in part 3 of the project called OpenDSS that's going to make it possible for us to look at the time varying nature of DER and how it's going to impact feeder operation. Another sort of study would be whether you're going to have any issues on fault detection, as I mentioned before. DER has the potential to desensitize your relays. And so basically, if you have DER further downstream on the feeder, given that the DER is going to contribute to the fault, that means you could have less current coming out of the substation, less current that your top of feeder relays is going to see. And so this isn't the topic for our class. This is more the topic for a class like 581. But this could also compromise your protection as well. You're going to get maybe transit over voltages when you have faults or due to capacitor switching or other switching activity. One event that we talked about is transformer switching inrush. This is something we cover in IEEE 587. We don't get into this here because this actually requires a different type of computer code that could actually solve differential equations. And so we can't really do this with Windmill or OpenDSS. It takes another program type. Simulink could do this. We're looking at harmonics. Not only have harmonics injected by the inverter, but harmonics could actually be synced into the inverter filter due to existing harmonic sources on your distribution feeder. And then you also would need to get into contingency analysis. So basically, is there going to be any problems like restoring circuits because load's going to be a lot higher after it's been off for a while? It's called the cold load pickup. You have to worry about whether you can backfeed properly or not during emergencies. And this is going to put any restrictions on feeder reconfiguration. And so remember, in the reliability, we talked about the fact that you might have a couple sources. And then what you may want to do is you might want to actually have the ability of transferring load from one circuit to the next. So if you have a fault here, then maybe what you could do is if you have like a tie switch, say here's your tie switch over here, then you could open this switch and you can close this tie switch. Well, what happens if you have like DG out here, just some distributed energy resource device? Is that going to muck up your ability of switching load back to another substation if you have to worry about what's going to be the impact of that DER on that switching operation? And so this is something else you could look at as well, is this is maybe compromise your ability of trying to improve reliability through circuit switching. Another thing you get into too, and which is a little bit beyond the scope of this class, is the impact on system stability. This would be more for like the 100 megawatt scale units you connecting up to the transmission grid. However, in the future, if each distribution substation had, say, like 20 megawatts of PV, this might add up to the point where we even have to consider distribution PV on transmission stability. And so there's a lot of different things that would go into these interconnection studies. And normally each utility has kind of like their hot points as far as what they need to include based on their system characteristics. And what you'll see is over time, when they run different studies, you'll find you could use like the last study as a template and kind of build off of that, and then maybe add a few things that you've found based on field experience. So a lot of times you're not really doing this from scratch. You can go back to the last interconnect study and use that as a kind of like a starting point for what sort of things you need to look at. One thing about time varying PV plant characteristics, again, we're going to use another computer program called OpenDSS for this. But one thing you just have to be aware of is that the output of PV is not some nice little curve like that as a function of time. It doesn't peak out in the afternoon and stay there, right? It could actually have, because of cloud cover conditions, kind of some unpredictable characteristics. And so Electric Power Research Institute, which is a research organization funded by utilities, actually has a website that has some sample data sets. They have some sample feeders in this OpenDSS tool format, as well as data for PV all the way down to the 1 second level. And what's kind of interesting about this is you can see that even on a completely sunny day, the output's a little fuzzy, toward the top of the curve. There's always some deviation in irradiance. And so you do have these full sun days where you have a small variability, but then you have these cloudy days, especially when you have variable cloud cover, where the output can drop rather dramatically. And kind of what I've sort of seen is it doesn't go all the way to zero, but it could actually drop down by about 70% from its peak condition to its minimum condition. So this, could actually drop down to maybe 30% of nominal. In very short periods of time, maybe like in tens of seconds. And so what this looks like when you blow this up and you kind of focus on certain times a day is you see this output drop, and it comes up and it drops down, it comes up and drops down. And what this does is this causes a lot of issues with rapid voltage changes, or what we called like flicker before. And so this is something you have to look at, as to what degree is this variability going to cause problems with flicker, that's going to be an issue, or interact with the operation of line voltage regulators. And so this is the sort of thing we're going to look at part 3 of our semester project, and what's going to be the impact of the variability on, say, like voltage regulation. So as I mentioned before, as far as the study cases you're going to run, you usually start with a base case without DER, because if the circuit already had problems, you're not going to penalize the interconnection of a interconnection request to somebody because the circuit already had existing problems. I mean, basically what you may want to do at the beginning is maybe get the circuit back operating within specifications. But what you're kind of looking at is, to what degree does DER make it worse, right? And so you got to have a baseline. You have to kind of know how the circuit's currently operating, what are currently voltage deviations and equipment loadings, and what's kind of going on with line regulator, capacitor operations, because maybe there's already like a high annual count of regulator operations or capacitor operations just because of load conditions on the circuit. Then what you would do is you would then, once you have your base case, then you start looking at adding the DER project. And again, you would look at peak winter and summer days. Then you also look at light loading conditions, which are typically spring and fall. And then you would maybe run some base cases and you superimpose the DER on top of this. A lot of times what you'll do is you'll look at loss and restorage of generation cases. So if the PV trips offline or comes back on, what's the step change in voltage and stuff you're going to see. And then you also look at intermediate operation due to cloud cover, let's say if it's going to be a PV plant, or gust of wind if it's going to be a wind facility. As far as contingencies, you have to factor in, well, what would happen if you had a sophisticated bullet bar control if that went offline? And then, is there going to be impact on feeder reconfiguration if a fault occurs? Is having the PV or the DER plant out there going to hamper your ability of restoring customers? One thing I want to mention here is that voltage regulator modeling is really key. And we talked about this in class as far as a set point in the bandwidth. And we also talked a little bit about what should happen if, we have like reverse power flow. But one thing I didn't mention is how we coordinate line voltage regulators. And the way we coordinate voltage regulation is through what's called time delay. And so what you do is usually your substation voltage regulation has the shortest time delay. If all possible, if we have a large change in load, let's say, and that's going to cause a change in voltage, we normally would have that taken care of at the substation. In this case, these taps are all going to be changed the same. It's a three-phase operation. You may just look at one-phase voltage, but all taps change the same. We want to make this a three-phase operation. When we get downstream, we can have independent phase operation. So it's three single-phase regulators operating on their own. And what we do in order to coordinate these devices, we give the downstream device a longer time delay. So we give the station regulation a chance to operate first, and then we would operate the next downstream device. Then if you have a voltage regulator below that, then you would add more time delay. Now I'm showing a PV location below that regulator number 2, but a lot of utilities are very wary of putting PV below a line voltage regulator. And so like Duke Energy, they typically wouldn't allow something like that, because then what that can do is that can cause extra operation. So in our project, we're going to take a look at this. We're going to see what the impact's going to have on the regulator counts. But just want to point out here that, if this is going to be above a certain size, they typically wouldn't want to put that below a line voltage regulator. So as far as mitigation options, what are some things we could do to fix problems? And again, if you have a perfectly working circuit and a developer wants to add DER to it, the DER operator owner is basically going to have to pick up the tab for these circuit upgrades. And so as part of the system impact study, what you can also suggest is what these upgrades could be and what the cost is going to be. And so things we could do would constitute like circuit upgrades. Some of these could get rather expensive. So obviously, we want to balance the circuit load out, and you're doing that in part 2 of the project. We could maybe reconductor. So if we reconductor and put in larger wire sizes, we won't get as much voltage deviation, but that's super expensive, but maybe that's what we have to do. Kind of what a lot of utilities like to do is run what's called express feeders or express taps, which I'll show you in just a little bit, where basically we kind of give the DER facility its own section of feeder, so it doesn't interact with the rest of the feeder. We can also relocate line voltage regulators. We can relocate capacitor banks. We could add more units out to the field if necessary. We can also do things on the control side. We could maybe play around with our voltage set points. If we have line drop compensation, we can play with that, or the bandwidth. This is kind of limited. I mean, to some degree, if you change the bandwidth to 2 to 3, you might fix the problem, but you lose the ability of regulating voltage. And so this isn't something that can commonly be applied. but it may work in certain situations. The other thing we could do is if it's a line voltage regulator, we could set it up in cogeneration mode where it could take power flow in the opposite direction. And maybe we have to upgrade the controller for this. So sometimes what you have to do if you have a circuit that has really old controls on it, you have to go in there and put more recent controllers out there to give you the functionality you need that's a little bit more friendly to DER integration. Something else you can also do too, which we talked about, is do some control with the DER inverters. We couldn't really do this with the 2003 standard, but with the 2018 standard, these newer inverters we're putting out there are going to have a lot more functionality. Something we could do is we could operate at leading power factor. That would actually help drag the voltage down. Leading power factor means you're basically absorbing bars, so that counteracts the real power you're injecting. You could do this reactive power control or dynamic bar compensation, where what we're going to be doing is adjusting the reactive power input as a function of the voltage. And then there's some situations where you might force a DER installation to curtail its real power output in certain reconfiguration conditions. And so if it's a 2 megawatt facility and we can't handle that for reconfiguration, but maybe that could be curtailed down to 1 megawatt during these restoration conditions, that might be something we would impose as well. Protection and communication upgrades. A lot of utilities like using what's called transfer trip. So what this means, if you have a substation with a breaker, if you have a downstream DER, that if that circuit breaker operates at the substation, you send a direct communication signal to that DER to make sure it goes offline. That's pretty expensive. There's probably ways we can do that with the inverter settings or some local protection, but some utilities would require that. And there's also like advanced protection functionality we could utilize as well to make sure the DER hangs in there when we need it to, or trips off when we know that there's no way that that's going to be recoverable. And then some other things from the distribution management system viewpoint would be to have volt var control that's set up to work with DER. So this volt var control could maybe send signals to the DER inverters in order to help manage the voltage on the grid. Something else that's being talked about quite a bit is using battery energy storage systems. And so when you see this deviation in power injection, that could be smoothed out by having energy storage. So as far as these upgrades, see a lot of utilities like having their large scale PV at distribution level separate from the regular feeders. The recommendation may be to run what's called an express feeder. Actually, the developer would pay for this. And so you could actually connect up directly at the substation in this case. Another thing you could do is if you have a large scale PV, and if you aren't allowed to interconnect below a voltage regulator, is you could have what's called an express tap. And so it's not all the way to the substation, but you pick some point that's above the voltage regulator, where if you connected this point, you won't cause issues with interference with voltage control or too large of a voltage swing due to like cloud cover. And so this is something else we're seeing quite a bit of, these express taps, where we figure out in the study, we don't have to go all the way back to the substation. We pick a point on the main backbone that we can connect into where we're not going to interfere with the rest of the feeder. So again, the developer would have to pay for this express tap as well. For the smart inverter functionality, and we talked about this before, there's a lot of different sort of control options. There's like a power factor adjustment you can make. So you could actually have the inverter operate at a lagging or leading power factor. So this would automatically adjust the reactive power as the real power output change. We've got these settings for low and high voltage ride through. So if there's voltage sags that are caused by faults, we can make some adjustments in the settings for that. And then you've got this ability also of adjusting reactive power to possibly compensate for short-term duration flicker. So if the PV is actually causing the voltage change through variable real power injection, what you could actually do is you can actually monitor that voltage and have the Q output track that, so it kind of counteracts it. All right, so that's something that's being looked at. And we talked already about the volt var control and the volt watt control, the droop characteristics we could implement as well. So we've got kind of like this functionality now with these smart inverters that we didn't have pre-2018. Unfortunately, a lot of these legacy systems that were installed before then don't have this control capability. And so it's only been recently that we could really take a look at this additional smart inverter functionality. And this kind of shows you this relationship, which is based on the K factor. So if you have a real power injection and an imaginary power injection, we could think about this as a real current versus imaginary current injection. Again, this is going to interact with the resistance and reactance of the interconnection impedance. The real power interacts with the resistance, the reactive power interacts with the reactance. And so if we have enough reactance in the line, then we could actually counteract the voltage change due to the real power of the current. And this shows this, again, this curve where we can actually adjust these set points right here. So, if we decide, that we want to do something, even between the 99 to 101% of the voltage reference, as soon as we're outside of this band, then we could even change the slope of the reactive power injection with respect to voltage. And the slope would be a function of the system impedance. So anyway, as far as this right here, we'll look at that in part 3 of the project. We'll actually look at whether we can adjust this volt var control on the inverter to counteract the flicker that's caused by the cloud cover. I mentioned before that you can use battery energy storage for helping to smooth out the variable output of DER if it's intermittent due to wind or solar. And this shows a design for a large-scale battery energy storage device where we have the batteries in racks. This is a DC. Maybe we have a DC to DC step up, and then this is hooked up to an inverter, which converts the DC to AC, and then we interconnect this into the grid. And so if I have a signal from the DER, what I could do is I could take that to figure out how to charge or discharge the battery to basically smooth the net output. And so this shows an example where you have PV output and it's cycling up and down. But what we do is when the PV output drops, we have the battery energy storage system inject to counterbalance that. And when the PV output goes back up, then we have the energy storage device charge. And so this kind of shows an example of doing that and what you can do as far as having a net output, which is smoothed. And you can see that what would happen is the batteries would be charging and discharging as needed in order to counteract this. And so this is why a lot of developers are starting to look at combinations of PV plus storage, because then if utility has an objection to the rapid voltage change that could be caused by installation, then they can add a certain amount of energy storage to sort of counterbalance that. That adds more cost to the project though, but in certain situations it may be merited because you can use the energy storage for other things as well. As far as different limits you use in studies, we talked about like the 3% rule for rapid voltage change. This is kind of changing with time. This NREL handbook that I have is one of the reference, gave some numerical guidelines in here for this. But again, this is kind of changing with time. And so this is just an example of what some study limits could be. I'll give you some limits to use in your part 3 of the project. But just as some examples of some of these different things you would actually use in your study as criteria. So anyway, just to kind of finish this off, there's a lot of different references out there that you can take a look at. As far as getting solar data, if you need to get typical sites like in North America, this is available from the National Renewable Energy Lab. There's actually a site that has data you could use. EPRI, the site I mentioned before, has some 1-second data, which is kind of interesting. And the smart inverter specifications, how these units are operated, is actually kind of coordinated by what's called SunSpec Alliance. It's a trade organization that works with the various PV equipment vendors. And so they're kind of leading the charge as far as inverter functionality and what should be included. As far as sample studies, and I talked about some of these before, NREL has a high penetration integration handbook that was written in 2016. This is probably getting severely outdated now, given that we've learned quite a bit about high penetration circuits, but it has some good material in here. And then this 2014 report that was co-written by Southern California Edison, it had some early concerns of what we were looking at in these large scale PV interconnections. And so these are some, I think, some useful learning documents. There's another guidebook that was recently published by NREL and some other agencies that kind of talk about what's really needing to be factored into DER interconnection. This is kind of like a state-of-the-art survey, and so this is kind of useful reading. And then, and RECA, which is a research organization for electric co-ops in the United States, in conjunction with Leidos, which is a consulting company, came up with a PV system impact guide, which was written, or it came out in 2018. What's interesting about this is this has a number of sample system impact study reports in the appendices. So you can actually see what these reports look like and how they actually wrote this up. So you'll be kind of doing some of these studies for part 3 of the project, but you're not really writing this up in the system impact study format. But if you're curious and think this is something you may want to do, a lot of consulting companies have folks working on this sort of thing. You can get some examples of what these impact studies look like. And then finally, as far as some of the local Duke Energy criteria, there's actually a document from 2017, and they call Method of Service Guidelines for DER no larger than 20 megawatt, which talks about some of the criteria that Duke uses. And what Duke's been doing is they've been using this system stiffness as a guideline as well, because they found out if the system stiffness drops to a certain point, then they found historically that they're going to have issues with some of these interconnections. And so they talk about the use of the stiffness factor of 25%. But anyway, what's kind of interesting about this is this was actually written by John Guida, you may know as a guest lecturer for this class, and also a lecturer in the 581 class. So anyway, we've gone through a lot of material here, and like I say, the intent of part 3 of the project is kind of expose you to some of this system impact study analysis, at least for a couple of the criteria we talked about here. And we say we're going to have to switch to another tool called OpenDSS where we can look at this more effectively, because a tool like Windmill does not allow you to look at the dynamics properly. And this is where we're going to use OpenDSS for that. So the next lecture that I'm going to use is actually going to be on OpenDSS. I'm going to cover that in the next lecture. And then after that, and then I'll wrap up the DER by kind of giving you some examples of analysis that you can do in Windmill versus analysis that you would do in OpenDSS.